but it is suspended in the propellant. So it is also coming under the disperse system or the liquid dosage form. So the major category which we are going to have in our pharmaceutical development in the formulation is solid dosage form, liquid dosage form, and semi-solid dosage form. In the liquid dosage form, we have got a solutions, more homogeneous systems and heterogeneous systems. In the homogeneous system, we have got a solution syrups, and they are clear liquids like eye drops, ear drops, and large volume parentals of homogeneous state. So these are all going to coming under the solution, whereas the suspensions and emulsions, colloids, and your SNEDs, these are all going to coming under the disperse systems. So this is actually a toughest part in developing it. Most of the times, this disperse system has got a very tough point which will be given to the pharmacist, a formulation scientist. They have to undergo a lot of pains to make the product successful. That is the reason, if you are able to see this particular type of dosage form got the success, if we are able to know it, and we can be able to understand easier dosage form like solutions and solids and semi-solids, they will be made very much easy. So we are going to deal this disperse system. In your syllabus, you have got disperse systems and SMEDs. Both are present in the pre-formulation studies. So how to handle them, we will see. Later onwards, we will be having an individualized approach to see remaining also. And we have got something more concepts which will be elaborated in that particular unit. We will see them. So the first thing is we need to know what is the disperse system. The disperse system is referred to as a system in which one substance is dispersed phase is distributed in the discrete units, that is separated entities. So that separate entities are the discrete units. They distributed throughout the second substance, that is called as a continuous phase or dispersion medium. So this is actually containing two, that is the reason it is containing and going into the category of heterogeneous systems. So this heterogeneous system is containing the two phases. One is dispersed phase, another one is a continuous phase. So the dispersed phase can be any of the phase. Each phase exists in any solid or liquid or gaseous state. It means even a small bubble which may be dispersed in the liquid, we are going to get a micro balloons. So there the air is entrapped. And in that micro balloon, you may get the question what gas we are going to do. It is not that we are creating a void and gastro-retentive system and floating duct delivery system we are going to have. In the liquid, if it is dispersed in a continuous phase, liquid is dispersed, we call it as an emulsion. If solid is dispersed, we call it as a suspension. So in the emulsions, we have got again category of self-emulsified drug delivery systems, sets. In the sets, we have got again two categories like SNEDs and SMEDs, like self-micro-emulsifying drug delivery system and self-emulsifying, nano-emulsifying drug delivery system, SNEDs. So these are all the things which are coming under the broader category when your dispersion phase is categorized and varying with the type of states of matter which is putting as a dispersed phase. So we are going to cover a lot of combinations of them. The concepts what we are going to learn, it will be applicable to so many dosage forms with a little bit criticality is present in some cases we need to apply. Remaining all going to be the same. So these are all aware, you might have already studied in B Pharmacy level itself. Without any problem, you can understand this part, but we will be going little bit by knowing what is it is going to communicate, and we are going to see the critical aspects of the pre-formulation one by one. So something maybe repeated will be present as it is a first class. I don't know what is the level. We will be going in a slower pace only. And so that you will be having any difficulty or adjustment with the pace, you can give the feedback in the WhatsApp so that we will be accordingly turning into the different phase of flow of teaching. Now, if you see all the categories, they can be divided further into different types of dispersions. They can be classified. If you see the one is molecular dispersion, another is colloidal dispersion, another is coarse dispersion. This coarse dispersion will be having particle size greater than 500 nanometers, and it will be having sometimes which will be having visible to the microscope. Under the visible microscope, it is sufficient. Whereas the molecular dispersion at the top, which is having the size lesser than the 1 nanometer, and it is actually appearing rapid diffusion and invisible in even electron microscope and ordinary ions, and they will be seen with criticality, and they will be very less. It is appearing as a solid solutions only. They will be appearing as a solution. At the molecular level, they got distributed. That much they will be having. Whereas colloidal dispersion is in between 1 nanometer to 0.5 micrometer. They diffuse slowly, visible in the electron microscope or ultra microscope. So they will be studied and taken the surface characteristics, everything can be possible. So these are all the wide categories which we are going to have it in our formulation development. Of course, we know that coarse dispersion is going to give us the trouble and easy to manufacture. Molecular dispersion will not give us trouble because it appears as a solution, but manufacturing is very tough. So when you are making very easily, you are going to have a lot of troubles. If you are making with difficulty and you are facing and making a technology available, then you are going to have a long lasting benefit, and you are going to have a thermodynamically stable emulsions or disperse systems. We are going to get it. So this classification of dispersions based on the molecule, that is particle size, is going to give us a broader category of how to handle these systems. So if I'm making any one of these systems which I wanted to start, we need to keep in the pre-formulation itself. So what is my aim of doing this particular formulation as a disperse system? So either I need to make it as a molecular dispersion or colloidal dispersion or coarse dispersion. I need to decide first. So accordingly, we need to proceed for the further development. So this is depending upon what type of drug we are handling, what is the molecular weight of that particular drug, and solubility of the particular drug in the medium. These are all going to be taken into the account while selecting the what type of dispersion I am going to make it and launch in the market in the pre-formulation stage itself. So this is very much mandatory, and see this particular classification of observing all disperse system based on the particle. All the three in the suspensions, then we will do all the three types of sizes in the emulsions also. So molecular level, and this is at the colloidal level, another one is a coarse level. So these are all the things which we are going to deal in each category of suspensions also, emulsions also. So what is suspension now? So we are categorizing dispersion into major broader category like suspension and emulsion. Now we are taking suspensions. Suspension is also a disperse system. The disperser phase is solid and is distributed in a particulate form throughout the continuous phase, that is a liquid. So according to the particle size of the disperser phase, again they will be divided into the colloidal dispersion and the coarse dispersions. Most of the times they will be varying. If it is at the molecular level, if it is getting dispersed, then we will call it as a solution only. Don't get confused. In the dispersion of a suspensions category, if the material is dispersed at the molecular level, it is going to entering into a solution state. So we are going to have a colloidal suspension, another one is a coarse suspension, depending upon its molecular size, that is particle size. What are the properties of good pharmaceutical suspension? Now you may be knowing that when you are selecting a suspension, your drug is present in the solid form. If your drug is present in the liquid form, we are going to choose an emulsion. Solid, and the solid is insoluble in nature. Most of the times insoluble nature is pertaining to the water, because water is a universal solvent. We are going to give this as a solvent most of the times, preferably because of its inert nature. So generally we will have this dosage form in the disperse system like pharmaceutical suspensions only when compared to remaining combinations. So if you are choosing that, yes, my drug is solid, I want to put it as a disperse system because I have got a problem of compression of that particular powder. I have got a delay, or it is taking longer time to get disintegrated or entering into the system available in form of a tablet or a capsule. And I don't want to give the pain to the patient by giving in form of an injection. So in that particular case, even though it is insoluble, I will be making that particular drug available to the patient in the form of suspension. So this is the decision which will be critical. Means I am not going to give as an injection parenteral, even though it is immediate because it is painful. Solid dosage form like a tablet and capsule, it is taking some delay in the disintegration. Because of that, there is a time gap or lag time is present for the execution of the action. I don't want that. And it is not possible to get a good compressibility, and it is a little bit appearing costly also. So it is better to launch, especially for the patients like pediatric and geriatric patients, like old aged patients and children. So this is actually the best dosage form I need to select. And in the pre-formulation studies itself, we are going to take this decision because this dosage form will not going to choke the throat when compared to other solid dosage form. So it will not choke the throat. That is the reason I am entering into my journey to make this particular drug as a pharmaceutical suspension. Now I need to have a target or the endpoint set. So for that purpose, we need to see the idealities of that particular delivery system, and we need to target it, achieve it. Even we are appearing to the near to that, it is good. So the first category in this particular properties of the good pharmaceutical suspension or ideal characteristics are ready to redispersion of any sediment which is accumulates on the storage. We cannot avoid to form the sediment because it is a dispersed phase and gravity is present. Because of the gravity, the solid will tend to come down. We can't avoid it because it is a universal principle. But at the same time, if you are able to redisperse it, even though it is forming as a sediment, I can meet the good suspension. And even in the redispersion also, it should be redispersed after the gentle shaking. It is not a vigorous or equipment utilized shaking. It is not required. Most of the times, the redispersion should be attainable by shaking gently. If you are using any equipment and it is taking hours or days together to redisperse it, that dosage form will not work, because you want to take the medicine now and you need to shake it for half an hour. It is highly painful to you and it is not having any advantage of skipping your capsule and tablet. That is the reason after gentle shaking, the medicament stays in the suspension long enough for a dose to be eventually measured. This is the prime requirement we need to see in our development. Another one is the suspension is pourable, because we need to give a labeled claim of certain amount of drug per 5 ml or 1 ml of that particular delivery system. We need to pour that particular volume without having a sedimentation problem, so that every 5 ml or 1 ml is going to contain same amount of the drug. And it should not have too much of thick in such a way that it is not getting emptied from the bottle and it is taking a lot of viscous in nature and approaching near to this semi-solid, and it is not pourable. So that should not be there. It means it should not be too thin, it should not be too thick. So if you want to make your suspension pourable, you want to make it less viscous, but it causes the sedimentation, you won't get equal dose. If you want to make too thick, it won't come out of the bottle and you are going to face the problem. Particles in the suspensions are small and relatively uniform in the size. This is very much required. And why it is required to be uniform, and we will see a little bit later. And why it is required to be small, you know that sedimentation will be not fast, so that the product is free from the gritty nature, and you have got an advantage of the same thing when are applying in the form of a lotion to the body in a local application. So the small is a prime requirement there to prevent a gritty texture. So this is actually what a primary requirements of any good pharmaceutical suspension we need to target. If you are able to make this, and like this, if it is able to do it, and we need to consider what parameters, and we need to keep them under the control, how to control them. These are all the things which will make the journey of pre-formulation fruitful. For that purpose, what I need to understand, what I need to consider in the pre-formulation stage. Now we are going to little bit entering into the science. Till now we have seen the art wise. So art of giving my medication. Now to achieve that particular art, you need to enter into a science. Say for example, if somebody wants to make a sculpture, A sculpture can be made by taking a rock and cutting it to a small pieces to get the shape of the face and making it idol. The same thing can be made by making a mold. So the mold has got some shape, melt the drug, melt the any metal, and the molten form of the metal, put it in that mold and cool it, you will get the particular shape. So in both the cases, you have got some art also, and in the both the cases, you have got some science also involved in it. Similar in the manner, we want to make a art of making our dosage form. We need to back up with a science so that it will be precisely, repeatedly, accurately, it is reaching my target without any problem. So merely knowing that what I want to achieve, because I don't want to give the patient trouble, but I need to know what is the science behind it. Now we are entering into the pharmaceutical sciences. So the art part is looking at a science part so that I am achieving it with surety and with evidences. Because any person who is having inspection of our factory or a firm, they see the evidence. So these evidences can be backed up by the science. So such things which we are able to understand, then we can attempt very easily. This is only the making your curriculum little bit tougher also. You need to understand this one as an important. So most of the times my students will ask me, sir, tell me the important questions in the end of the examination, when the examinations are approaching at the end of the curriculum. I would say these are all the going to be the theoretical concept make the in the exam very important. You need not ask any teacher. So they are having a fundamental concepts clear, you are going to get that questions. It means that whatever you are going to see in this particular slide and further, you are having very gravity in the examination, in the pre-formulation studies, whatever the question, you are going to get it. So I think if you are able to understand this gravity of in this particular exam and the curriculum, of course you are going to have the similar thing which will be rectified in the factory, where in the industry you are getting an appointment, or you are a formulation scientist and making a dosage. So you see these particular 7 parameters which you are having a concepts understood, your pre-formulation journey of suspensions are very much fruitful and easier. So what are these concepts? One is the interfacial properties, that is surface free energy. Another one is electrical double layer. So this is decided by the non-constant zeta potential. Another concept is called as wetting. Based on that, you have got a electrokinetic phenomena based on the above. Of course, there is a very important concept called as a DLVO theory. And at the end, we have got a flocculation and deflocculation. If you are able to understand these concepts properly, you are able to handle the pre-formulation of the suspensions properly. And you may be getting as a ABC, and you are maybe getting a complete theoretical considerations for the pre-formulation studies of a disperser systems or a suspension dosage form. Then you need to answer all these things. Then you are going to get around 14 marks question. So around 7 points are there, each having a 2 marks contribution also. If you are able to write it all, and you will we are going to get 14 marks without any problem. So this is the theoretical aspect which we need to be considered for the suspension making for the pre-formulation studies. Once you have adjusted and taken care of all of them, our journey is very much smoother, and we are going to attain our targets of ideal suspension. First parameter now, interfacial properties and surface tension, what we have seen in the previous slide, the first surface free energy and the interfacial tension. So the large amount of the interface is involved in the formation, which in turn affects the stability of the suspension. Why it is large? Because the suspension has got a smaller particle size when compared to your tablets and granules. So you have got a lot of surface area. Because of this, you have got an interface between your continuous phase and dispersed phase is very high. So that is going to affect the suspension preparation stability. So the interfacial properties therefore play an important vital role in modifying the physical characteristics of the dispersion. That is the reason we need to consider them with due care. The second part which we need to understand in this interfacial property is surface free energy. So what is this? How I am going to handle it in the pre-formulation stage, and so that my journey over the market in the formulation development and in the selling selling of the product, that is in the shelf of pharmacy store, it is going to be fruitful. Because once you are making our dosage form, it is going to cross the R&D production, and it is going to the shelf of pharmacy store and reaching the patient home. Ultimately, it is entering into the site of action, and it will act. So now this is very much critical for the suspension is a surface free energy. It is giving that delta G is equal to you have got interfacial increasing the surface, whereas the delta T is given as an equation equated to the one is point is got delta A. So the delta A is the surface area. Most of the times the suspension, when you are making it very finer and finer to avoid sediment, that is actually what we have seen in the previous cases of the slides. So when you are making a finer and finer powder, you are going to enhance this surface area more and more. And when you're increasing the surface area, if you see this particular equation, delta G, that is surface free energy, is directly proportional to delta A. So the change in the area will increase the surface free energy. So when the surface free energy is enhanced, so your emulsion is going to be the thermod. So the smaller the delta G, the more the thermodynamical stability of the suspension. If you see where the trouble you are going to entering now, so you have got some conflict here. What the conflict is, you want to prevent the settling and you want to make the stable suspension by decreasing the particle size. When you are decreasing the particle size, so finer and find the change in the area is lower and lower, there is an increasing the delta G, that is free energy also more. So you are changing the surface area, there is a change in the surface free energy. So that is the reason you are going to have enhancement of the more and more the surface area by decreasing the particles smaller and smaller. Because when you are decreasing the small particles smaller and smaller, and you are enhancing the surface area more and more. When surface area is increased more and more, surface free energy is also increasing more and more, and your thermodynamical stability of this suspension is lesser, because the smaller the delta G, the more dynamical stability. So this is actually what the trouble we are facing in our formulation development. One way we want to increase the stability, another way we are affecting the stability by ourselves. So it has got one more term, gamma. This is interfacial tension between the solid dispersion, solid particles and the dispersion medium, that interfacial tension. This has got some more parameters which we'll be having. This is not in our hand because it has the material characteristics. How to handle this is a little bit furthermore we are going to see them, and what are the parameters which you are going to have, how it is going to affect our wetting and the surface tension of a solvent, how these parameters we will see. So this interfacial tension between the solid and dispersion medium is more, and surface free energy is more. If interfacial tension is going to be less, then the surface free energy is less. When the surface free energy is less, the stability suspension is more. So we want to decrease the interfacial tension. So this interfacial tension most of the times decreased by adding a surface active agents. They are acting at the surface of your solid and the liquid interface. When you are having this added, then you are going to reduce the interfacial tension, then we are going to have better stability. It means even though we are decreasing our particle to the lower and lower level, enhancing the surface area, we can keep by maintaining another term, that is interfacial tension lower, so that we are going to attain the surface free energy lower and lower level, so that we can attain the suspension stable. So this is actually the fundamental we need to learn, otherwise our journey of preformulation. A system with very fine particle, the most dynamically unstable because of the high surface area. So these are all the conclusions, and we are making it. You can write the same thing in the exam also. So what I have told orally. Does the system tend to agglomerate in order to reduce the surface area? That is the reason particle growth will be there. So thereby the excess free energy will be decreased. Surface free energy may also be reduced to avoid the agglomeration of the particle, which can be accomplished by the reducing the interfacial energy. So when the wetting agent is added to the suspension formulation, it is absorbed at the interface. This will result in the reduction of interfacial tension, making the system more stable. It means we are decreasing the particle size, one aspect, even though it is causing a damage to us and making a agglomerate, we are preventing it by reducing the surface interfacial tension. This can be done by adding a wetting agent. So this is actually what we are adding as an excipient now. So till now we are dealing our drug and continuous medium, both are inevitable. And now we are making an excipient introduced to get a stable suspension. This excipient is now only one, it is appearing now. Later onwards, some more going to be added. What are them? We will be seeing. Wetting agent. It is difficult to disperse the solid particles in the liquid vehicle due to the layer of adsorbed air on the surface. Most of the times, if the particle is having a enclosed surfaces and pores in it, so that will have a tendency to float onto the surface like meniscus. So above the meniscus, that is actually onto the surface. They won't entering into the bulk of the solution. So we need to remove that particular air so that they will be having denser, and that will cause the suspension to enter, that is particle to enter into the bulk of solvent. So it is actually what we need to understand here. These wetting agents, they adsorb onto the surface, evacuate all the air, so they make it more dense, and they will make the suspension to that solid particles enter into the bulk of solvent. Thus the particles, even high density, float because of the water, that is air present on the surface of the liquid, until the layer of the air is displaced completely by the wetting agent. So the use of wetting agent allows to remove the air and surface air from the surface, and allows the easy penetration of the vehicle into the pores, so that you will be getting a stable suspension. Otherwise, you are going to get all the suspended particle floating onto the top of your medium. Powders which are not easily wetted by the water, so they are accordingly show the larger contact angle, and such as example as a sulfur and charcoal and magnesium stearate called the hydrophobic. They are in nature, and they are going to have a problem of wetting, and they tend to float onto the powder, even though they have got a density high, that is heavy particles are there, but they tend to float it because of the entrapment of the air. So this problem is obviously present in the manufacture of our formulation. This is the reason what we do. Generally, when you are making a suspension, you make like a paste first with a continuous phase containing some wetting agent. That paste is redistributed or reconstituted with the continuous phase to make up the volume to the level we want to make it. So this is actually what the problem during the manufacture. I think you may be understanding the same thing in the kitchen also. So when you want to make your Horlicks or coffee or some Boost or Bonvita, generally preferably if you see the milk powder or Horlicks mixed with milk, what will happen? The milk powder or Horlicks tend to float above the water. So it makes a lot of problem to distribute it. So what your mother or yourself is going to do is you need to scratch with a spoon. So you not avoid it. Your grandmother, what she always goes, she adds initially less quantity of the water or a milk as a continuous phase, and makes a thick paste, and making it further redistributed with adding a further continuous phase, and easily a problem will be solved because of the floating is not there. Otherwise, when you are putting your spoon, the floated particle tend to come out of your surface, and they will not be getting mixed properly. You will have a clumps. So this clump prevention will be prevented. In the similar journey, what we are going to do here also, we are going to make in the pre-formulation studies how much volume of the continuous phase which is containing wetting agent to be decided, so that to prevent this particular problem. Powders which are wetted by the water, like hydrophilic in nature, they are zinc oxide, and most of the times it is given as a talc, but zinc oxide and other material, they will not have any problem. The wettability of the powder may be ascertained easily by the observing the contact angle and spreading coefficient. So what are these two, and how to make them reduced? So how to increase the spreading agent and reduce the contact angle? So this is actually our question of particularly we need to handle for the wetting agent problem and selection. See this particular diagram, you are able to understand the particle which is floating onto the surface, of the liquid. So it is not at all dipped in this, if you are able to see it. I'm always telling, if you have got any doubt in between also, you can interrupt me and you can ask me the doubt there itself, because we are a little bit going a little bit deeper when compared to your regular one. So your concept need to be clear now. So in this particular case, if you see here, what is happening? So it is difficult to disperse a solid particle in a liquid vehicle due to the layer of adsorbed air on the surface we are having it. Because of that, the material tend to float onto the surface of the liquid. So the liquid, when it is floating above the solvent, so that solid particle floating above the solvent, the contact angle is going to be very, very high. So you see that the tangent which is drawn at the solid surface, then it is taken from the plane of your liquid, the contact angle you are going to get. So this is the angle between your surface of the liquid and the tangent which is drawn to the surface of the solid. The intersecting point, you note that and find out the angle. That angle is going to be your contact angle. So in this particular case, the wettability of the powder may be ascertained by usually observing this contact angle and the spreading coefficient. So what is the spreading coefficient? And we have seen the contact angle. What is the spreading coefficient also we will see. Now, imagine the situation where the particle which is having a less air by adding your wetting agent. So initially, without having any wetting agent added, it has got the contact angle above 90 and it is tend to float in the solvent. Or you are putting your liquid onto the surface of a flat surface of the solid. So when it is not spreading, it will have the contact angle where the plane of the surface, angle between the plane of the surface and the tangent of the liquid globule, that can also be taken. So in the poor wetting, this angle is very, very, very high. In the good wetting, the angle is reduced. It complete wetting, this is completely zero. It means the particle is getting synced into the continuous phase, or the liquid is completely spreading onto the solid surface. This is actually what the concept is. You are decreasing your contact angle so that you are making better wetting. If you see this particular one, Young's equation is going to have the very good importance in this particular case. You have got in this particular graph, if you see, there are so many interfaces are present. So one is gamma SV, that is solid vapor, that is means solid, and the gas, that is extreme right. You have got another one is a slant line, that is a tangent to your liquid, that is actually gamma LV, that is liquid vapor interface, that is gaseous phase and liquid phase interface. There is another one which is present in the x-axis, that is the solid liquid interface. So the distance, that angle between the gamma SL and gamma LV is called as your contact angle. So this is actually the contact angle is a theta. The theta is having a relationship with whatever the relationship between the three axes, what we have got. If you see here, gamma SV is equal to gamma, that is solid vapor interface, is equal to gamma SL plus gamma, that is liquid vapor interface, into cos theta. So this is actually what, depending upon your theta angle, you are going to have the variations of this. So if this equation, which will be making the what is the surface free energy of each particle at their interfacing with another phase, like whether it is exposed into the air or is exposing in the liquid. So what is its interface? So if you see the gamma SL, the suffix SL is the solid liquid interface free energy, whereas the gamma SV is solid surface free energy. If solid surface free energy is lesser and lesser, the contact angle is going to be lesser and lesser. So this is going to be reduced. So this job will be done by wetting agent. So this is gamma LV is equal to liquid surface free energy. So this have an interface, one liquid with the vapor, solid with the vapor, that is gaseous state, and solid with the liquid. So this one, which will be having a wetting agent concept, which will making this contact angle and lower, makes this particular possibility of making a good suspension. Most of the times, what type of wetting agents I need to choose so that my wetting angle, that is contact angle, is going to be getting lesser and lesser. There are two things which are required to be seen, like hydrophilic colloids, like such as acacia, tragacanth can act as a wetting agent. They are water soluble, water loving, and however care should be taken when using these agents. They are promote the deflocculation if they are having a structured vehicle concept. Another one is what is that we will see a little bit later. You might have already understand the structured vehicle and thixotropy. So we will be having this concept also learned later. There is the intermediate HLB, that is hydrophilic lipophilic balance surfactants such as polysorbates, queens, and sorbitol esters like spans. They are used to for the internal preparations, and sodium lauryl sulfate and this is actually another surface, that is clear tincture is used in the external preparations. So we need to select typical wetting agent for the oral, that is internal use, and that is external use, like lotions and the solution applicable onto the external use. Accordingly, we need to take it, because when you are interchanging them, we are going to have a problem of giving that particular medication, because when you are taking certain one which you can be given only external preparation, we cannot choose that into the internal preparations. Solvents such as ethanol, glycerol, that is glycerin, and the glycols, they facilitate the wetting. Most of the times they will be added to enhance your powder. So yes, few drops of them which can be added to your solid, and they will be made as a wetting with these solvents. Then you add a continuous phase, and they enhance the wetting. Reason is they remove all the gaps in the pores and the surface of the solid and remove all the air from that place by adding these solvents. And the solvents are water soluble in nature. The moment you are adding continuous phase, the wetting can be improved easily. So these are all the concept which you are using as an improving the wetting agent. It means adding a small traces of the solvent one so that your gases are expelled. Intermediate HLB surfactants which we are using, queens and spans, and sodium lauryl sulfate and any surface active agents. And we are using also hydrophilic colloids. They are also having a wetting agent property. Now coming to the concept called as a spreading coefficient. We have seen the wetting part. In the suspension, it is very much critical in the interfacial phenomena. Another one is spreading coefficient. So what is the spreading coefficient? How it is required to be handled? If you see the spreading coefficient, it is containing three parameters. One is delta S, that is sigma S, that is surface tension of the solid. Sigma L, that is surface tension of liquid. Sigma SL, that is surface tension of the liquid minus liquid and solid interface. So these are all the three which are present. Surface tension of the solid minus surface tension of the liquid and minus surface tension of liquid solid interface. So these three terms which are present, it is giving the spreading coefficient SC. So in this particular case, so for the convenient, the value of the spreading should be positive. It should not be negative. In the above terms, if you are thinking that it is a positive, what will happen? You are going to have a spreading coefficient. It need to be in the positive value. So it means your surface tension of the liquid and the surface tension of the solid liquid interface, it should not be dominating than your surface tension of the solid. So to have your positive value. If you are having, these are all the liquid surface tension and the solid liquid surface tension is very high, dominating, and your surface spreading coefficient is going to be in the negative. When the spread negative, then you have got a poor wetting. This is actually what we need to see, the surface phenomena of what the solid and liquid we are going to use. This can be done by adding our interfacial surface active agent that will be acting at the interface. So they will be reducing sigma L, sigma SL, so that we will be having a positive value of spreading coefficient. So the suspension is more stable. This could be achieved by the modification of the value of the surface tension of several surfaces included until positive value of the spreading coefficient is reached. But how to do this? So generally we know that this can also be done by adding the wetting agent, what we have already seen previously, spans and tweens. So they are the intermediate in nature, near HLB value of 7 and 9. So they will be going to solve the lot of problems in these suspension making. We are going to select it to enhance the spreading coefficient. Now we are going to entering into your disperse system drug, and we have got a wetting agent. But we need to solve what is the problems which you are going to solve with this is the sedimentation, thermodynamic instability, and the wetting problem will be solved. So for that purpose, we need to study or evaluate our suspension during the formulation development in the pre-formulation stage itself. That is actually what we are introducing later as a in-process control test. So these in-process control tests, it will make our journey of making regularly in our factory, so that I am going to yield a better suspension that is present in the shelves of the pharmacy store. So how to make this and how to evaluate it, so that I am making as an in-process control and making our journey of formulation manufacture smoother. So one aspect of the physical stability of the pharmaceutical suspension is concerned with keeping the particle uniformly distributed throughout the dispersion. That is one. It is making the clumps without making agglomerates. While it is seldom present to prevent settling completely over the prolonged period of the time, it is necessary to consider the factors which influence the velocity of the sedimentation. So what are the most of the times we are keeping in the shelf without touching for 2 years of shelf life. Maybe if somebody is not asking, even in the pharmacy store, we don't touch even that particular suspension. It is kept untouched for longer period of the time. During that time, it will be getting a settling and it may fall the compact cake. So we need to avoid that, and we need to avoid the rate of settling sedimentation, avoid and make it a very slow pace, so that we will be having a better stability and easy reconstitution, redispersion generally. For that purpose, we have got a principle called as a Stokes law. The Stokes law is already known to you. We need to make it memorized. We need to consider this is linked to our velocity of the settling and the sedimentation formation. So this is the formula. So the rate of settling is, that is rate of sedimentation is d square within brackets density of the solid, density of the solvent multiplied with gravity, acceleration due to gravity. The whole term is divided by 18 into eta, that is viscosity. So here, if it is seen, the viscosity of the dispersion medium is having an inversely proportional relationship with the rate of settling or the sedimentation. So if you increase the viscosity, settling rate will be decreased. And if you decrease the viscosity, settling rate is increased, because it is having a inversely relationship. It means that we are going to add in our suspension now to consider the problem of settling by adding viscosity building agent, we call also thickening agents. So now after wetting agent, we are adding a thickening agent, viscosity building agent in our suspension in the pre-formulation stage. So the second term is when diameter is more and rate of settling is more. It means we want to prevent the settling, I need to decrease the diameter. So for that purpose, I am making my particle smaller and smaller. So this is another one I need to consider during the pre-formulation studies. So what is my diameter of the particle which I am going to distribute? I need to decide now itself. G, I cannot change it because it is acceleration due to gravity cannot be changed, because our product is to be sold on the earth only. It is not in the space or it in the deep mines. So on the earth surface, G is always same. So I cannot touch it. But one more thing which we are going to handle is density of solid and density of solvent. So even I don't want to touch them also, because they are the intrinsic property of the solvent and the solid. But what can I do is I can select a solid and a liquid combination in such a way that I can have a least difference between them. But generally my solvent is water and the drug is fixed already. So density wise, I don't have any option to change intrinsic properties. So I don't want to handle this particular property now, because I don't want to change my continuous phase to reduce this. But I can do the reduction in the diameter, increasing the viscosity. These two we are going to handle most of the times in the pre-formulation studies. So we don't want to have handling of G, that is acceleration gravity, changes in the density of suspension. So now fourth component is entering into our journey of suspension is thickening agent. So we have got a drug, solvent, wetting agent. Now we are introducing another one is thickening agent or suspending agent, or it is also called as viscosity building agent. Now